So, welcome back, everybody. We'll start the first talk of the day. Our speaker is William Stein from University of Washington, and he's going to talk about sums of modular symbols.
Great, thank you. So I'll be talking about statistics that you get associated to modular symbols. And this is basically some questions involving how modular symbols behave viewed from a slightly more statistical perspective than normal, at least initially, motivated by some questions of Barry Mazur and Carl Rubin, which are related to understanding the behavior of Selmer groups of elliptic curves as you vary over various number fields. So here's an outline of the talk. I'll just do some quick background about modular symbols and L functions. Then I'll talk about the most kind of obvious statistical question you might ask about modular symbols and our total ignorance about it. And then I'll talk about another slightly less obvious question you might ask and make a conjecture. So first, here's some background. I'm going to leave this slide up on the side. So we have an elliptic curve, a modular form f associated to it. I'll denote the Fourier coefficients by a sub n. There's a period mapping, which is a map from P1 of Q to the complex numbers, and it takes an element alpha, so a rational number, or I infinity, to the integral from I infinity to alpha 2 pi I f of z dz, which is a complex number. There's a period lattice, which you get by taking all closed paths and integrating inside of the complex numbers, which is nicely, well, the elliptic curve over the complex numbers is isomorphic to C modulo that period lattice. This is all like 19th century mathematics. There's an action of complex conjugation on the period lattice that breaks it up as a direct sum of a plus and minus part up to an index of possibly 2, in case the period lattice is rectangular or not. And we're going to consider the modular symbol, which is a map from P1 of Q to the rational numbers, rather than the complex numbers, associated to the elliptic curve. And for this talk, I'll just talk about the plus modular symbol, but there's also a minus modular symbol. And what you get is you just take, given an alpha, if you map it over to the period lattice, or to something sort of almost in the period lattice, it might not quite land in the period lattice, then if you add it to its complex conjugate, you get something that's real, and it's some multiple of the least real period. And that multiple is the modular symbol. So to an element of P1 of Q, you associate a corresponding rational number, which is the multiple of the least real period you get by integrating from I infinity to alpha, and symmetrizing, that is, by adding to its complex conjugate and dividing by 2. Okay? So to every elliptic curve over Q, you have in this very natural, canonical way a map from P1 of Q to the rational numbers. It's not necessarily easy to compute. It can be slow to compute. Basically, the way it works is that there's a one-time computation, which is polynomial in the conductor of the elliptic curve, roughly O of n cubed in space and time. Once you do that calculation, then you can evaluate this modular symbol fairly quickly. But that initial calculation that you need to do to get things going can be very slow. If your curve has conductor around 10 to the 10, you're out of luck. So it's a reasonable sort of thing to do for curves of conductor up to about 1 million. But of course, you can define it and consider it in general. And this is exactly, like this one object determines, for example, the p-adic L function attached to the elliptic curve. And it determines the L function of the elliptic curve, all kinds of other behavior. Okay, so, and I'll leave that slide up because it's kind of the definitions. So here's an example. I'll switch and compute this live. Okay, so define our elliptic curve. Just for fun, here's a plot of this particular elliptic curve. And here's what the period lattice looks like. It has a real period, and then there's a non-real generator, so it's not rectangular. And there's a function modular symbol, which gives back the map that I just defined. It sends infinity to 0, and it sends other rational numbers to rational numbers. So let's just take a rational number. You can make up any rational number you like. How about 5,077 divided by 2,015? Just take any number you want. Wow, it's a funny coincidence. So it's not a completely random function taking an enormous number of values. It's actually kind of challenging to get a lot of different values out. Let's just look kind of systematically at the sort of numbers that we get. Notice the denominators seem very controlled. You're never going to get a denominator bigger than 10, as it turns out. So the denominators are either like 1, 5, or 10, or 2, possibly. You don't see that here, I don't think, but I guess it could happen. And you can see you get a bunch of numbers out. And there's some symmetries here. Like, notice that you start here and over there, they're the same. So you have some symmetry. Okay, so that's the function we're going to consider for the rest of this talk. Given an elliptic curve, there's a function that basically sends rational numbers to rational numbers. You get a bunch of rational numbers associated to an elliptic curve. And just to record some of the symmetry that one finds, which just comes from basically how integration works and the transformation properties that a modular form has. This one's really easy because am plus, this is by definition taking the thing from infinity to a over m and the thing from infinity to minus a over m and adding them together. So you get the same thing if you put a minus there, because you're adding together exactly the same thing in a different order. Addition is commutative, and there's one other slightly less obvious symmetry. Okay, so given these two symmetries, you really only need to consider the values of this modular symbol between 0 and 1, actually between 0 and a half. But for as a consistency check, I'm always going to consider a whole bunch of values of this modular symbol between 0 and 1. And you should always double check that the values at the end are kind of symmetric with the values at the beginning to make sure we didn't mess something up. Okay, this is just a quick motivation slide. Why might you care about modular symbols? And this goes way back. So, by the way, modular symbols are defined by Birch in the 60s in conjunction with understanding the Birch and Thornton-Dyer conjecture. He defined them in one of the papers in which he introduced the conjecture to try to do calculations with it. So they go way back. They were used a lot by Manin and Mazur and other people to define p-adic L functions and study. They're really just like a tool for studying L functions. But one example reason why you might care about modular symbols is that if you consider the twist of the L function of E at 1 divided by some period, then you can write that as an explicit sum involving Gauss sums and these modular symbols. So this function that I just defined attached to an elliptic curve from the rationals to the rationals encodes all the information you need to understand L functions of twists, at least the zeroth derivative, so the value of the L function at each of these points. So if you're going to try to understand, say, statistical behavior of this, then it's useful to understand modular symbols. And so a very naive kind of take a step back and don't worry too much about L functions thing you might do is just consider this set of numbers. Given an integer m, so just evaluate the modular symbol at 0 over m, 1 over m, 2 over m, 3 over m, that collection of rational numbers, okay? And you'll get a whole bunch of rational numbers out. Ask how they're distributed. So that's actually the question Barry first asked, because he and Carl had some conjecture about how these guys behave, and it assumed something about the distribution of these guys right here. So one approach, as you learned yesterday, to trying to understand the behavior of L functions is random matrix heuristics. But one problem with them is that they don't necessarily prove anything. And you often want to actually prove things, and so you might want to replace those heuristics by much more down-to-earth, concrete, closed heuristics that depend on some behavior that might have some hope of actually proving. And so that's what Carl and Barry are motivated to do. Okay, so that's the background or the motivation. So let's look at the first kind of naive thing you might do, and I'll switch and just do it live. So I'm just going to take all these values. This is a bunch of code to make things fast, or at least to load some code that makes things fast. And what I've done is I've evaluated, I just went quickly. This is a frequency histogram of the values of the modular symbol for the elliptic curve 11a at 1 over m, 2 over m, 3 over m, etc. I just evaluated that function at all of those rational numbers, got a whole bunch of rational numbers out, and drew a frequency histogram. Normalized so that the area under the frequency histogram is 1. So it's a distribution, probability distribution. Okay, so that's the sort of picture you get. It doesn't look like a nice, clean, normal distribution. And we can go further. So it'll probably take under 10 seconds to do it up to 1 million. I hope. Okay, so again, it kind of looks kind of hard to understand, but that's what it looks like. Let's look at how many different values we got when we did this. So I have to actually reevaluate that. So there are only 38 different rational numbers that came out in the image of evaluating at this enormous number of inputs. Okay, so it's a really small number of different outputs that we're seeing. Although if we increase the number of things that we look at, let's try going up to 2 million, which I hope should only take about 6 or 7 seconds. This is all being computed live. Let's just see how many different numbers we get. Oops. 41. So, you push it really far and you get a couple of numbers. And you get a histogram that looks like that. It's kind of messy. I don't understand what that histogram looks like, actually. So it's just the same thing I just showed you. So sorry, I can't tell you what the answer is. I don't know what that distribution is in the limit. There's some, hopefully, distribution in the limit. As you let m go to infinity, maybe that picture starts to look like some very specific probability distribution. I simply don't know. I'm asking that question. I'm not sure it's a good question. I don't know the answer, but it doesn't look like it's just nicely, cleanly converging to some nice normal distribution or something. Okay, I don't know. So let's consider another question, which is perhaps funner to draw pictures of. And it turns out maybe has a really nice answer, although we can't prove it yet. But I will convince you that it does. Surprising and nice answer. So just taking exactly the same collection of numbers, the modular symbol attached to a fixed elliptic curve, and you can do this with any elliptic curve at all. And I'm just going to pretend for the moment that if I fix the denominator m and consider the modular symbols a over m, for a going from 0 up to m minus 1, that maybe I can think of it like I'm generating a bunch of random numbers, a bunch of rational random numbers. And I can make a random walk and just kind of record where that random walk goes. So I start at 1/5. So that's 1/5. And then I add minus 4/5 to it, which is the next number I get out. And then I add 17/10, minus 4/5, etc. So you get like a random walk. You could almost pretend your modular symbols, giving you the change in the stock price from day to day or something. And so this is what happens at the very beginning when you just look at, here I'm just looking at the numbers up to 12 over 13, s of 12 over 13. So maybe this is a great random number generator and we'll get really nice random walks and they'll have great properties. Or maybe this is a horrendously bad way to make a sequence of random numbers. Let's see. Okay, here's what happens with m equals 20. Notice there is some symmetry relating what happens on the second half to the first half. That's just a consistency check because the modular symbol is beautifully symmetric there. So you should expect that. I could have just deleted the extra half of the symmetry and then you wouldn't have seen that and you'd be annoyed because you'd be like, hey, the obvious consistency check is missing. I don't want to do that. Okay, so there's your picture for 20. And again, I'll switch and compute it live. So this is just what I showed you. Let's try it for a bigger value, say 100. Notice the pictures are kind of looking similar, just more refined. So you kind of are getting a basic shape there. It's getting nicer and nicer. Let me just change this to 200. Remember what it looked like? Looks pretty similar. Change it to 500. So it kind of looks like as I make m bigger, so now I'm evaluating the modular symbol at 1 or 0, 1 over 500, 2 over 500, etc. I'm getting a picture each time, and it's different because like the range of the x-axis is different, the range of the y-axis is different, but the picture basically looks the same from value to value. And if I change to a prime number, let's see if it's kind of an arithmetic phenomenon or not. No, it looks basically the same. 500, the next prime after 500, looks almost the same. So the natural thing to do at this point is to think, well, maybe we can normalize the x-axis and the y-axis so it's consistent between different values of m. And then maybe, the natural thing is maybe there's a nice limiting function. And we're just looking at plots that approximate it. In particular, this would be a terrible random number generator. And on the other hand, you'd want a nice formula for whatever the limit is. Okay. Maybe just push this a little further. 10,000. It starts to get slow this way, so I wrote some more efficient Python code for computing the same thing that's dramatically faster, actually. But this is what it looks like. It's just kind of looks exactly the same as you increase the value of m.
Could we be missing something because of the lack of scale along the x-axis, though? This sort of almost fractal nature of the up and down, or could we be?
Could be. Turns out we're not, but yeah, we could be, but we're not. I mean, of course, the program is just, it's always rescaling it to the same width. It's just labeling the numbers differently. So anyways, they all kind of look the same. And if you choose a different elliptic curve, you get a different picture, but again, they look consistent from one m to the next. It's just a slightly different picture. Okay, so just to summarize, the pictures all look the same, more or less. And by the way, you can generalize what we just did to arbitrary new forms of weight greater than or equal to 2. So, except if the degree of the form is bigger, if it's not a rational new form, so it has coefficients in a bigger field, then you more naturally get a random walk in quotes, but in a higher dimensional space. So this is a picture of what one of those might look like. I haven't done anything with that except draw a picture of it. Okay, here's a few different elliptic curves, so you can see. So 11a, that's the one I just showed you. Here's 37a. So actually, I'll show you more than one at once. Okay, so that's 389a, and this is 37a. So they look similar, but they're not identical. And this is where I've evaluated the modular symbol at a million different points and made my random walk. Okay? Let's see. So that's the sort of picture you get. And the question is, what is that a graph of? Because, I mean, if you keep increasing m, it just looks the same. So it surely goes to some limiting function. What nice, clean limiting function is it? So here's what you do to normalize things so that I basically, when I define f sub m of x, I'm just rescaling it so that the pictures are all comparable. So that's what I'm doing here. And make a conjecture, a very natural conjecture, to make the limit exists. Maybe we don't know what kind of function it is, but let's just conjecture that the limit exists, making no claim about the behavior of taking the limit. That should be an uppercase m. Okay. So now, in my remaining, I have a few minutes, I'll tell you what I think the limit is and why, and convince you that it is that. So let's let omega plus be the least real period. So that's the thing that the modular symbol is multiplying. The modular symbol is the rational number times that is equal to the integral. So that's the least real period. And a sub n, again, is the new form. This is what that limiting function is, I think. It's 1 over 2 pi omega plus times the sum an 2 pi nx over n squared. So that thing that I drew over there for 389a, if you compute the Fourier coefficients a sub n attached to the elliptic curve 389a, and then explicitly try to compute that infinite sum and plot it, you're going to get that picture. Okay. I will try to convince you of that in 2 separate ways. Way 1 is I will numerically show you, which is probably way more convincing. Okay, so this is some code. The code I wrote right there draws the plot that's scaled so that the x and y axes are all comparable for various values of m. This complicated looking code is very tricky Python code to give me about 100 times speed up so that I can evaluate that infinite sum So I can evaluate this infinite sum to some precision very, very quickly. Okay, now let's just do an example. So what this just did, in red, that's the trigonometric sum that you see over there. And in blue, the actual plot you get, evaluating the modular symbol at 0, 100th, 200th, etc., and then making the random walk. So they don't look too close, but that's the same basic shape. However, let's just change it from 100 to 1,000 and see what happens. So now we're evaluating the modular symbol at more points, and it gets a lot closer to the conjectural limit. Okay, and then change it to 10,000 and evaluate. It's getting even closer. Change it to 100,000 and evaluate. And it's even closer. You can barely tell the difference. It's a little bit different right there. Change it to 1 million. And they look, okay, so there should be no doubt in your mind that sum over there, at least numerically, looks like when you plot it, you get the same thing as plotting the sum of modular symbols with appropriate normalization. Okay, so that's the numerical.
What does the difference look like?
That's a great question, and if I had more time, I actually had a second half of my talk which I deleted, which is all about the distribution of the difference. And Barry really hoped that it was normally distributed, and you can, but it actually looks really funny. Like the distribution has a piece in the middle, and then there's 2 pieces on the outside. So it's very much not normally distributed. Okay, so now I will explain to you. I will give you a heuristic argument of Barry's, which is theoretical, which is a reason that you should believe that trig sum over there equals the sum of these modular symbols. Okay, and it's a very compelling argument. So the basic idea in one sentence is that the modular symbol is, after all, the integral from I infinity to alpha. And it is a really annoying thing to evaluate because you're integrating this infinite sum an e to the 2 pi I n z, and you can't switch the order of integration and summation. Because if you try to do that, it doesn't converge at all. Like basically, you try to evaluate your e to the 2 pi I n z with z a rational number, and you just get a huge sum of things and it doesn't converge. So you can't do that. But what if you just replaced alpha? So the modular symbol, you're going from I infinity to alpha. What if you just replace alpha by a number with positive imaginary part? Then that does converge. You can switch the order of integration and summation. Converges really nicely. So you just get an explicit infinite sum which equals that almost modular symbol. So you just kind of extend the notion of modular symbol, but to endpoints are in the upper half plane. Okay, and then what you do is you just consider, instead of evaluating at 1 over 0 over m, 1 over m, 2 over m, 3 over m, you just move everything up a little bit and evaluate at that plus some small imaginary number. And each time you do that, you get a very explicit answer. And in fact, the answer is exactly what I've written down right here. It's that. It's an infinite sum. I got that just by evaluating the modular symbol, but I moved up by I times eta, so that the modular symbol went from really freaking annoying and involving, having to do things like split paths and use modular symbols relations and all kinds of crap, to, you just switch the order of integration and summation. And you get, for every real number as you go sideways, 1 over m, 2 over m, etc., or whatever, you get this explicit real number, which you could approximate. And then what you do is just integrate that from 0 to some point, and you can integrate it. It's an infinite sum that converges pretty well, so you integrate it, and this is what you get, which is almost exactly what I wrote down over there. So the integral from 0 to b, after we've moved everything up a little bit, of our modular symbol is this explicit formula. Now, how do you compute integrals if you're just learning about the definition in calculus? You use Riemann sums. So if you approximate this integral right here with a Riemann sum, where the points that you're sampling at are like 1 over m, 2 over m, 3 over m, etc., you get something that looks almost the same as the random walk that we're considering. So that's the next slide. So I just recopied from the previous slide, and now I evaluate so that integral from 0 to b of x plus I eta plus, so that's my modular symbol moved up a little bit. If you were to take a Riemann sums approximation to that, it would be very, very close to this. This is purely heuristic. We don't know this because moving from a little bit above the x-axis to the x-axis, things go really crazy. So this is not proven at all, but if you just imagine that you could evaluate this integral using this Riemann sum, kind of cross your fingers, then you get something that's very close to this. And if you let eta go to 0, So if you just let that, so you're a little bit above the imaginary axis, so things converge. If you let eta go to 0 in this formula, then this just gets replaced by 1, and you end up with the infinite sum, that I conjectured that the random walk converges to, which is right here. So all you do is just replace eta by 0, and you get this. So it's kind of a, 18th century argument for what that random walk looks like. We don't have a rigorous way of justifying this, but it's clearly right because I gave you an 18th century argument and I gave you a 21st century numerical suggestive piece of data, but I haven't given you any proof at all. But there are a lot of good questions related to this, especially generalizing, doing the same thing for the minus part for higher degree, etc. With that, I'm done. Thank you. Yes?
From a non-expert perspective, I'm a little surprised that it's so hard because aren't there theorems that say that...
Oh, I don't claim that making this rigorous is at all difficult.
Okay.
I just claim that we haven't done it yet.
I see, okay.
I think it's probably trivial. I mean, we just haven't done it yet.
Okay, because I was going to say about,
it's like spare time.
typically if you have like a power series which converges conditionally on the boundary of degree of convergence, you can typically some kind of limiting argument. So maybe that's what happens here. I don't know.
Yeah, no, I mean, I have no doubt it's easy. But I just don't want to claim that I've done something that I haven't. So, yeah, sorry if I didn't make that clear. Other?
Do you have a plot of the difference? Is that something I'm just kind of curious?
Yes. Oops. So this is the distribution of the differences. So I do have that. It's not exactly the plot of the difference, but it's a little bit less information. But or I mean, it's normalized against the area under its 1, and so the differences are at most about 0.2 or so. And I'm not telling you which difference this is, but I guess I have m equals 10,000. But it doesn't look like a nice normal error term. It's a little funny. I don't understand what this is at all. Yeah, sorry. Oh, yes, Niels.
Well, you did see in the picture before as well, and I think you can read that out from Professor Code, is that as you increase your m, you're approaching your limit curve roughly from the inside, right?
Yes, I guess I can just, like right here. So, I don't know. Yeah. No, I guess not.
Okay. The first one's though.
Yeah. Yeah. Nope. Sorry. Yeah.
Any other questions?
Okay, thanks.